Hi friends, welcome back to our next set of videos. So it is the next video in the sequence that we are going for backpropagating these gradients through fully connected layers. And in last video, what we saw that we used our make moves library to create a fake data set on which we can use these classifiers, some neural networks that we created using NumPy library. So let's do a quick recap of what we did in the last video. So we had this utility that make moves, and that is coming from scikit-learn, and that is helping us to create number of samples, random samples, and it is also helping me classify them as two distinct data sets. So you see that that's how we plotted this data set. Now this data set we have bucketed them into two different classes. So all the red ones that you see, that's one half part of the moon that is falling into one class, and the purple dots are part of this data set that is falling into the next class. And what we intend to do here is that we are trying to train a neural network model that has got just one fully connected layer. And we declared some of the variables like dimensionality. That was 2. It means that we are having this two-dimensional data set. And then we defined some of the parameters for our single layer neural network, and then we ran it through number of iterations by trying to first calculate that what happens if you feed this input into the weight that you randomly generated also using the NumPy, and then you took the exponential of the scores coming out from the first dot product, and then there was logits operation where we did the probabilities, and then we calculated the loss based on the final softmax operation that we performed on the output. And then there was some regularization loss adding, and then we back propagated all these gradients through these layers, that is the softmax layer, then the fully connected layer, and we tried to optimize these weights by applying these gradients and using the parameters. And that's how we optimize these weights. And once the training was over, then we just generated some random points in the same space, and we used the model to classify them. And then we saw that how we are able to use the model to classify these two different data sets into different boundaries. Now, we discussed in the last video that why this model is not yet perfect, because it is not able to completely, uh, create a very fine line between these two data sets that's white and black here. So in this video, what we are going to do, we are just going to go to a little complicated model. We will try to add one more layer to our original neural network. So let's do that. So what we are trying to do is that we will say that create a two-layer softmax classifier. And here, let's go on defining all these parameters. So first is our regularization, and that is already defined, but I will do it once more just to make this example complete. And this learning rate is quite simple. We have just taken the value as 1, and let's define a hidden layer. Now, once we are trying to complicate the model, we are also going to add number of neurons to our fully connected layer. So this edge parameter that I've added, it is kind of signifying the hidden layer. So it's number of neurons that we'll come to know about. So let me add my first layer, and when I say first layer, I need to define a random weight that I'm going to optimize when I train this model on this data set. And I'm going to use my random NumPy, random rand n, and here I need to define that what is my input dimensionality. So this is first weight that gets multiplied by my input, and input is 2-dimensional, or the number of dimension is d that we have defined as 2. And then so these are number of rows for that matrix, the two-dimensional matrix that we are defining for weight 1. And the number of columns is what we call as edge hidden layer, or what we call as number of neurons for that layer. And then we will add a bias for this layer. So again, that would be again random, and we will start with zeros as we did in our last neural network model. And then comes the next layer. Again, I will try to do that on the same lines, but the only difference is that now it is going to take input from our first layer. So let's add second layer. So this is going to take input from the first layer. And that's why when I define the dimensionality of this, I need to make changes by trying to adapt to the earlier layer. So first dimension is going to be h, and then the k. So k is number of classes that we have to actually classify them into. And add bias here again, zeros, and the dimensionality is going to be 1 by k because k is the output number of classes. And let me see if I have already defined this k. That should be capital K. Well, it's already there. So we have two classes to make Moon's data set. We have created two data points, and we have two classifications for that, two classes for that. And that is what we are trying to do. We are going to come up with this two-layer model. Now, as we did in my earlier one-layer model, what is the usual operation with these neural networks? That first operation is first you need to get the score from the first layer. So I will before calling that as score. So let's try to call it as with a different name. So I call it with name say hidden. That would be the output from the first layer, and that will be simply the dot product between your input and the first set of weights, that is the first layer. And we add the bias, and what we also do here is that we let's add a ReLU layer. So it means that we need to squash all the outputs that is coming from this layer that is kind of very low. Let's try to squash and make it 0. So only thing that I need to do is that anything that is having negative value, I'm just going to take maximum of 0, and this output. So this output is going to be negative, then that is going to get replaced by 0, and that what ReLU layer means. So we call that as ReLU. And then further let's and then we go for the next layer. So now next layer we are going to calculate the same way. We are going to take that hidden output from my earlier layer, and I am going to do a dot product between the output from my previous layer with the second layer weights, and here also do the same thing, add the bias, and then the score that's coming out from this, that's going to go into softmax layer, and we again follow the same softmax process. And for that we need to take the exponential of that. So let me quickly take the exponential of this scores. So we call it exp scores that we did in our earlier one layer classifier. And now let's go to the next step, where now we have to take the probabilities so that we can normalize it across one of the classes. So we take the exponential scores, and what we need to do is that we need to divide it by the sum of all my values of exponential scores, and I have to do it across the rows. That's why when I do the summation, I need to define the axis as 1. So this is my axis, and I need to keep the dimensions same. That's why I will add one more parameter so that my dimension does not get altered, because I'm doing the reduce function here. Now, once I do that, then I just need to take a log of these probabilities, because that is what my categorical cross and propi loss calculation demands. So I need to take negative log of all my props. If you want to get good explanation of all these things, you can refer my earlier videos. Now, earlier we also said that we do not have to actually take probabilities of all the outputs of my matrix. So if my matrix is going to be 3 by 3, and only some of the values are going to be 1, rest are 0. So we only need to actually take the log probability of those values for which the true values are going to be 1. And so for that, what we did was that we used our all number of samples, and then we only went to those values in the actual output where the value is 1, not 0. And then let's go and calculate the loss. So once we have taken this log of probabilities, then we can quickly just go and blindly do the sum, because we have already flattened it up by doing this operation. So if I just sum, and for that I don't have to take the axis because already it has been flattened as a vector. Now we add regularization to this, and when we add regularization, then that regularization loss is going to be the standard formula, that is half lambda square. So lambda is reg here, reg, and then this is np sum. I need to broadcast these two things, and I also need to add the regularization from the second layer. So the same formula applies there as well. The only change is going to be, I'm just going to replace this weight 1 from weight 2. So this is my aggregate regularization loss that I have to add to my overall loss. So my loss is going to be added. I'm just going to add this reg loss to my actual loss that I just calculated. And then what I need to do is that I need to avoid this, avoid this exploding gradients. That's why I need to divide it by n. And if I do that, then this is going to reduce down the value of loss so that I can converge faster. And then I do the actual back propagation. And this is going to follow from our earlier back propagation exercise where we first assigned a parameter that was d score, and we started from our probs, and we discussed that what is the method by which we can backpropagate our gradients through the softmax layer. There is a very simple operation that we need to do when we take the probabilities. This step, we just need to deduct 1 from these values. So that's what we are going to do. So now when we have to calculate the score, first let's start with these probabilities, the output from the softmax layer. Then modify it by trying to just deduct 1. So once we do this, I mean, we have already done that differentiation operation through the matrix. And then I only need to do it for all the values that is having the actual value is 1 and not 0 for my hot encoded output. And again, if you have to refer to that, if you need explanation, you can always refer back my videos for backpropagation where I have explained that how do you backpropagate your gradients through the softmax. This operation is pretty much elaborated there. And again, once I calculate then I need to normalize it. That's why I'm going to divide it by n so that I can try to converge it faster. Now, I have to backpropagate. So my backpropagate through the backpropagation through the softmax is done. So I'm going to backpropagate it through the weights. So for that, what I need to do is that I first need to. So I'm already done till here. So what I need to do is that I have to go through the hidden layer, and for that, I would first calculate d hidden, and that d hidden is going to be the dot product between the d score. So from the chain rule, you are getting the differentiation, the gradients coming from softmax, then you have to propagate to the earlier layers. That's why you need to multiply this d score with what you get as d hidden. So this would be the dot product between the W2 weights. And if you understand what is this, then if I give you little insights into this, so what we are interested to find out is what is my gradient of loss with respect to this score, that is the score coming out from my first layer. So from the chain rule, if I try to find out, then this is going to be my d loss divided by dw2, and that's what I'm interested in. So here I have multiplied my d score, that is my gradient of loss with respect to score, with what I call as d score divided by d hidden. So once I do this, the chain rule, from the chain rule, what follows is I can get my gradient with respect to the weight 2. And then I do not need to do for all the values, so I only need to do it for only those values where I have suppressed it as less than 0. So I need to select a condition. I want to suppress it back because that's what the value layer is doing. Now, once that is done, then I can directly get dw2 by trying to do the dot product again. And here also the chain rule is going to follow. And I can get the hidden layer transpose, and I can use d score again. And if you want to understand what is that, then this is what we are calculating. And what we are interested to find out here is d loss by dw2. So we get dw2 here, and then we go to find out what is the gradient with respect to this bias. For that bias, this becomes quite simple. We just have to actually do the summation here, and here we will use d score. The axis is going to be 0. So it's like differentiating this simple function that is this with respect to b2, and that becomes equal to the score itself. So we can just use the d score from the previous step and just match it with the bias dimension, so that we just have to just do one sum. And similarly, we get dw1, that is again dot product of our x dot transpose. And why I'm writing these formulas directly, if you have to take reference, then you can go to my first video, and there we discussed that how when we backpropagate these gradients through a softmax layer where you have the input like this, then this formula holds. And yeah, you can just refer that. So similarly, we get the gradient with respect to the bias, and again we do the NP sum, and here it is going to be hidden, x is going to be 0, and now we just apply the gradients. And now to apply the gradients, this method is quite simple. Just use the learning rate and we multiply it, but we need to take the negative learning rate, DW1, and I'm just going to copy it 4 times because this operation is kind of similar. Only thing that I need to do is that I just need to change it from DW1 to DW2, and these will be for the biases. So the first bias, B1, and this is going to be B2, sorry, DB1, DB2, and this is going to be B2. See if everything works. That works. So now we have to run it for number of iterations. So whatever operations we have done, whatever calculations we have done from here, we just need to run it for a number of times. So we call that as a box. So this is in range 10,000. Let's suppose that's the standard number of iterations that we have been taken since last problems. And every time we calculate loss here, then we need to print it. So we say that we don't do it for every iteration, but we do it after a certain time. So we say that after every 1,000 iteration, just print this loss so that you can keep track that how the loss is converging, diverging. Your iteration number, that would be decimal, and then your loss, that is going to be a floating point value, and here it will be epoch and the loss. Okay, so let's run this. I think this 2 is going to go inside the loop. So when I do that, so you see that loss is quite high for the first epoch, and it's going down, further down, and once it converges fully, then now this layer is done. So my weights are optimized, these 2 layers are optimized, and next thing what we will do is that we will create our 2-layer classification function on the same lines that we did in our last video. And here we will again refer to the same operation that we did last time. So this is the usual feed forward operation. So for the predict layer, what we have to do is that we have to repeat this. So let's copy this common operation and paste it here. And the only change that I need to do here again is that I will go and change this actual x to x in, because that's what we are feeding to our function. And once this feed forward layer is done, then what we return is actual probability in which class this is falling in. For that, we need to look at the probabilities of the classification, and on axis 1, that is the row that is one of the classes, we have to return the maximum values that will correspond to my actual classification. Now I can evaluate my model, and I wrote the evaluate function for a generic model earlier, and where I can give the actual output that we generated from what is predicted by this 2-layer neural network. So we feed the original input, and we try to compare the actual output with predicted output here. And here again, the accuracy of the model is quite high. So now let's go back and again generate the mesh grid. So now let me define some number of points on my mesh grid. So standard one is that I go with 10 by 10 matrix for this, and for that I get a mesh grid in terms of xx and yy. These are set of points, and these set of points are then rearranged into a kind of a mesh that we visualized earlier. In the last video, you can go and look at what the mesh grid does. So quickly, let me try to write the mesh grid. And for that, we need to feed 2 range of values, and we will define the range of values using linspace function. So linspace, we just need to give the minimum and maximum value of the range, and then just ask that how many values between these two limits you want to generate. So let me give the lower range as the actual data points that we generated. So that is from the first dimension, and get the minimum, that's going to be the minimum boundary, and get my maximum boundary from the first dimension. So here this is, get me the max. max and give me number of points between these two values. The number of points is 10 here. Now I want to give it a little width, so let me reduce a small amount from the minimum and add a little bit to the maximum so that I can cover more range. And I do the same thing when I have to feed another parameter. So for that, I need to take the second dimension here. I do the same operation, but only thing that since the data is two-dimensional, the first range is going to be from the first dimension, the second range is going to be from the second dimension. And now once we do that, then we can just visualize these values. So let me take what is this, and you can also visualize what is in my YY, first 10 values from each one of them. And we also plotted it earlier, but we are not going to plot it here. We are just going to use our predict two-layer function. And now I want to actually create something that resembles my input that is two-dimensional. Now we have these two data sets, and for that, if I want to stack it vertically alongside, then what I need to do is that I need to use the concatenate function. And I have elaborated that again in my last video. So if you want, you can go back to my last video and see what the ravel function does, what concatenate function does. So I'm just going to use these XX and YY, and I need to also reshape it because my X input is two-dimensional. So I'm going to reshape so that it matches with what we have as my output Y. Now I can just plot these two things. So I'm use control function again, and this is my mesh grid, and this is my output. And then if I just say that, okay, what is my plot here, then I would have this kind of boundary. Now let me see that if I just overlap, I will just superimpose my original data set that came out from make moons. Am I able to draw a clear boundary across that? So if I say plot scatter, let me bring my original data set. So that is going to be X, and this is going to be 1, and use the actual output for the color maps. And to make it look better, let me go back to my plot library and let me get a good C map. So for clarity, let me use a simple one. Okay, so does not seem to be that good. Okay, because I did not use the predict two layer. So let me use the predict two layer. So now you see that predict two layer is using my two layer neural network. And so if I use predict one layer, this was my original output. And here we saw that some of the points that you see here, that is not falling in my yellow boundary. And some of the points that's here, that's falling into yellow, that should fall in my purple boundary. So now when I use the second neural network, and then I see that there is a clear boundary between these 2 points that is kind of separating them out quite beautifully. So that's how we can keep adding number of layers into our model, and that will keep me giving a better model each time so that we can classify these things better. So that's it in this video. Next time what we will do, we will try to create some more complicated data set as input. We will train this complicated two-layer neural network again with that new data set, and we will do the same steps again. That will be quick video, and then we can close this whole backpropagation series. Thank you. Thanks for watching this video.